Okay, so our next presenter, last for today, is Khoren from BetConstruct and also AUA alumni. And may I add that I have had the pleasure to be his professor anyway. So thank you for
So you're the only person who used the digicolor here. So it's happening or you live here? Oh, okay. 일어난 분이
마크로만 하면
Okay. Hi everyone. My name is Khoren, as already mentioned. And for the last year, me and the team of 3 researchers were trying to build an agent that plays poker better than humans. And I would argue this is one of the hardest ways to get rich. This might be hyperbole, but you'll say what you think in the end. So let's define what kind of poker are we talking about, because there are a lot of variations. But the one type of poker that was most interesting for AI research, and this was even mentioned in the seminal paper on Nash Equilibrium by John Nash, is no limit Texas Hold'em. And heads up means that there are only 2 players. No limit means that at any step of the game, each player can bet any whole amount of money, any integer amount of money, from minimum bet that has some logic that is determined by to all in. So we have a huge action space. We can conclude from this that we have a huge action space. The game is usually played amongst 2 players, which is called heads up, or amongst 6 or 9 players. What we tried to build is an agent for 2 players, because for 6 and 9 it's much harder. The game becomes much bigger. Let's discuss some properties of no-limit Texas Hold'em that will become more relevant as the presentation goes along. It's a zero-sum game. This basically means that if in any given hand I win X dollars, it means my opponent lost X dollars. This is an important property that gives a lot of good attributes to such games, and solving these kinds of games is much easier than non-zero-sum games, if the sum is not constant in particular. There is an additional fee for the house that conducts the poker game, but as far as our research was concerned, we just didn't include it, because it's just economic concern, not a research concern. It's imperfect information, and we'll talk much more about this, but it means that at any given state you don't fully know on the game tree where you are located. This is due to the fact that you don't know your opponent's cards, so you don't know exactly in what state you are in. This is much different than, say, chess or checkers, where you have full understanding of what's going on, what's the state, what kind of states will can proceed this state, and this is a very important distinction that we'll touch more on later. The game is enormous. It has more than 10 to the power of 161 unique decision points, where we should learn some useful strategy for. and this is more than the number of atoms in the universe squared. So you can't just brute force a solution to such a huge, enormous problem. This is as big as Go, I think. Okay. And for simplicity's sake and for research purposes, we set the stakes at the beginning of each hand to be equal. So if I start with the maximum allowed amount and you start for maximum allowed amount, because in real life, what limits users from buying in to the maximum is some economical concerns. And for research purposes, it was not that relevant, so we set each player to have equal amount of money at the start of each game. So solving this means finding a Nash equilibrium or finding a strategy that is as close to Nash equilibrium as possible. Imperfect information games are often overlooked and not discussed much because most of what we consider to be reinforcement learning is actually the study of Markovian processes. But Markovian processes have some important but pretty restrictive assumption which limits the types of interactions and games we can model using Markovian processes. For example, Markovian processes are almost all board games: chess, checkers, Go, Nardi, and backgammon. And something like negotiations, war, diplomacy, these are imperfect information games because you don't have all the information about the state of your opponent. So this entails a lot of other consequences. Which cannot trivially be mitigated with current RL methods that work well on perfect information games. Okay, most real situations are imperfect information, and war negotiations, financial markets. Not everyone knows who is going to buy anything. Before an IPO, you don't know what kind of financials a company has. So this is a very good real-life example of why it would be interesting to study imperfect information games as well. Turns out our current models that work well for reinforcement learning environments that have perfect information fail miserably on imperfect information games. People try to solve with PPO, with, I don't know, actor critic, poker, but it failed every time. And there is actually a separate algorithm that works best for these kinds of applications. Yeah, and this makes life much harder. Finding a Nash equilibrium for imperfect information games becomes much harder as a result. So what I mean by Nash equilibrium, to be more specific, I mean Nash equilibrium is a profile of strategies, so it's a set of strategies, each describing what each user will do with what probability in each state. So this is, if you are familiar with the nomenclature of standard RL, this is policies. So each player's policy is such that any given player has no incentive from deviating from its current strategy. In two-player games, it means that if I deviate from my current strategy, if I'm playing Nash with you, then I lose more than if I play by my current strategy. And this also means for zero-sum games that we will draw if we are both playing a Nash equilibrium strategy. We will at the end draw. I won't win anything, you won't win anything from me, we will end up at zero. This might seem disappointing, but actually this is theoretically the best you can do in the worst case scenario for two-player zero-sum games. And in practice, this is pretty good because humans are not good at calculating Nash equilibria for huge games. So if you can play Nash, most likely you will crush even the top humans. So I want to stress once more, because I designed the presentation in a way that would contrast this set of approaches from traditional reinforcement learning algorithms that all of you are used to working with. The imperfect information part is the difficulty imperfect information introduces was actually noticed by the founding fathers of this field. And if you read the seminal book on reinforcement learning from Sato and Bardo, they at the very beginning say we consider only Markovian processes and we don't concern ourselves discussing other processes, because these types of processes are very flexible and can model most types of interactions. This is true. You can engineer some way of designing your states so that your process becomes Markovian 99% of the time, but for some important applications like negotiations, trade, war, financial markets, you never can. Okay, so this assumption, Markovian assumption, is built in very popular reinforcement learning algorithms like TD learning. And they thrive in settings where the process is Markovian, and they fail in other settings. It's pretty hard to solve imperfect information games because it has some wild properties that we are not used to. For example, in a given sub-game for a perfect information game, you can only concentrate on solving this particular sub-game and ignore the rest of the game tree. So, for example, you can imagine this is the visual illustration. This huge pyramid is what game tree is. Imagine any trajectory alongside this pyramid to be one particular realization of gameplay. I do this action, you do that action, we end up in this shaded area, the shaded sub-game. This is all the sub-games that are reachable from this point. You can imagine this as some configuration on chessboard. So from this chessboard, not all other chessboards are possible to reach. But if you are solving chess, for example, you can only concentrate on this shaded area and not worry yourself with the rest of the game tree, and you can recover optimal gameplay from only concentrating on the shaded triangle. But for imperfect information games, some wild and unexpected things happen. Some parts of the game tree that are not even reachable from your current state can affect the optimal gameplay you should consider in your current sub-game. So this little light triangle is a sub-game that is not reachable from your current state, from your current cards, your stake, the opponent's action history, but you don't. But because the game is imperfect information and you don't know exactly where in the game tree you are, you have to plan and construct your policy in a way that takes into account even parts of the game tree that are not reachable from your current position. This makes life for imperfect information game solvers pretty hard, and I wanted to stress this point once more. This is very relevant because sub-game solving is very important in modern state-of-the-art RL agents. For example, consider the famous AlphaGo Zero. AlphaGo Zero actually learns a value function and then does Monte Carlo tree search to improve its current strategy. So you can imagine it. A good analogy to think about it is imagine you give your gut reaction whether this position is good or bad from the first look, and Monte Carlo rollout means you construct a subgame, you look several steps ahead, and you try to understand whether this which action will be good. Constructing such sub-games in imperfect information games is tricky because you have to consider all of the game tree sometimes. But this has huge implications because look here. If you just take the value network of AlphaGo 0, it's not that impressive. It has a low rating of 3000, but with added Monte Carlo tree search, it gets to 5000 Elo score. So this is very important component. And in imperfect information games, it's very hard to construct a good sub-game that has complete information to recover your Nash Equilibria. In 2017, first time was that researchers constructed a bot that could beat humans, and mainly their contributions were in this area of sub-game solving. So what was done on 2017? Finally, AI researchers beat the last hard problem in oral maybe. They constructed Libratus, which is an oral bot that played against professionals for 20 days. They had incentive in $200,000 of money. Whoever beats the bot with a larger margin would get more money. And they all failed miserably. None of them won against the bot, and the bot won with 99.97% statistical significance, which is actually pretty huge for a game with such huge variance as poker, because it's very hard to understand whether this win was attributable to luck or to actually good gameplay. The game is huge. Let's revisit this part again. Some variants, Rhode Island poker has 10 to the 9 decision positions. It was solved in 2005 using linear programming techniques. In 2015, Limit Texas Hold'em was solved, which has 10 to the 13 unique states. But No Limit Texas Hold'em was very hard to solve, and it took up to 2017 to be able to solve such a huge game. So what we need is to abstract the game tree, to consider less distinct situations, to be able to learn something reasonable in some reasonable amount of time. So the setup most researchers use is this. You have small blind, big blind of 50 and 100. Your starting stakes are 20,000, so you have 200 big blinds at the beginning. And obstruction is twofold actually. One type of obstruction is action obstruction, when you lump together a lot of actions and consider them to be the same, and card obstruction, when you group together a lot of card combinations and treat them the same. This allows you to compress your game tree to some reasonable size, which you can traverse and learn good policies on. The logic and the justification for action abstraction is that as far as optimal strategy is concerned, if you are betting $10,000 or you are betting $10,001, this shouldn't be very different from each other, and your policies should be pretty similar for both. And this is justification for grouping a lot of bet sizes into one and considering a bet of 10,000 and 10,001 as one single action. But this, of course, has some repercussions. The fundamental challenge of designing good action abstraction is actually similar to all RL applications. You have to have sparse enough representation that it will make your game tree small enough so you can learn some useful properties and converge to Nash. But if you make your abstraction too sparse, you risk learning some strategy that will map poorly to your actual game tree. So if you have too little actions, if you map too many actions to one, you will learn a useless strategy that is far from being good in real life. If you consider too many actions, your game tree size will blow up and you won't be able to learn anything useful as well. So this is very careful, this needs very careful balancing. And there are also other challenges, like how do you design an action abstraction that is coherent for different stake sizes, different situations. You have more money in this situation, less money in this situation. Do you divide it equally, equally spaced intervals? So good action abstraction is pretty hard. And one more consideration, if anyone wants to build the poker bot in the future, you should consider that action abstraction, if your action abstraction is dense in the upper levels, your game tree will blow up much faster than on the last round. So people use sparse action abstractions in the beginning rounds and denser as you progress down the game tree. I don't have much time to discuss this algorithm, but a good least exploitable, at least in theory, way of action abstraction, action mapping is called pseudo-harmonic action mapping, where you map your action to nearby actions with probability PA and PB. Imagine PA is imagine A is bet of 20,000 or 2,000, and B is bet of $3,000, and you have a bet of 2,500. Which action should you map this to a bet to can be decided using this mapping, and this was state of the art last time I checked, and we use this in our bot. Okay, the second part, very important, is card abstraction. This won't help you, this alone won't help you get a manageably sized game tree to be solvable in pragmatic time frame. You have to abstract cards as well. So abstracting means that some combinations of cards you consider to be the same and treat the same and learn the same policy for this or that combination of cards. This is done in two different ways that can be actually, these are orthogonal, you can combine them. Lossless or isomorphic abstraction, when you map a lot of combinations that are strategically the same. For example, if you have a pair of aces, it doesn't matter whether one was clubs or one was hearts, if you are pre-flop. So doesn't matter, all pairs of aces will be mapped to the same combination. And the second is lossy abstraction, where you just try to guess which cards would behave the same in a Nash equilibrium and map them together. For this, an algorithm called potential aware imperfect recall abstraction with direct inverse distance is used. The basic idea is for a couple of decades in this area, people were doing card abstractions, considering what would be the win rate against a uniform opponent if I was holding these cards, and then making feature vectors and doing k-means clustering based on this. What this innovation introduced was, instead of only considering the potential on the last round, it considers what's the probability of falling into this situation or that situation, which makes it potential aware. And Dirk Mover's distance, this was actually interesting. Dirk Mover's distance turns out is better at calculating distances between discrete probability distributions, which L2 distance or Euclidean distance fails. So this improvement allowed to build a superhuman level poker. Without this, it wouldn't have been possible. So when you are trying to construct an action and card abstraction, one practical tip I'd offer for you is just consider how much memory you can allocate. Then if you can allocate X gigabytes of data, consider your problem two-variable problem. A is the size of your card abstraction, and B is your size of action abstraction. They have nice property that they are orthogonal. You can configure them separately and they will work together. So you can consider this as finding a good A and B that will be reasonably big to model your card abstraction and action abstraction properly, so that A times B is smaller or equal to X, or your budget. So how do you train this thing? You constructed an agent, you did lossless abstraction, lossy abstraction, action abstraction, and you have manageably sized game tree. How do you solve it? You solve it using CFR, but to understand the CFR, let's consider info sets. Info sets are special kinds of states that actually contain in them a lot of other states. This is because you don't know in which game state you are, because you don't know your opponent's cards. So the set in info set refers to all the possible game states you can be depending on your opponent's cards. And CFR turns out works, and your game tree comprises of info sets, and you learn policies for each info set, not game states in this example. Okay. So let's consider this example. It's tic-tac-toe or chingachung in Armenian. Consider sequential configuration of this game, where first player chooses some action separately from the second player, then they both see each other's action. Here, P2 doesn't know where he is in the game tree because he doesn't know which action was performed by P1. This means that these dotted lines connect together states that will together construct an info set in which P2 can differentiate where he exactly is. So CFR works by minimizing your regret. Regret is a measure of how much you regret, how much better outcome could have you gotten had you done another action instead of what you have done. So this alternative action value is subtracted from the value of God, and you try to have such policy that your regret is as little as possible. CFR was proven to converge to Nash Equilibrium with because the average regret from all your iterations converges to 0. And interestingly, which was very shocking for me, you actually have to average the strategies along the path. So usually you start from a garbage strategy and you converge to an optimal strategy in RL. Here you actually take screenshots of your strategies along the path and then average them together, and the average converges to Nash Equilibrium, but each individual instance, no matter how long you train it, won't converge to Nash. There are some variants to CFR that can broadly be categorized into two groups. First group tries to okay, I have little time. First group tries to sample less action nodes, so instead of traversing the whole game tree, which is not practical for big games, so some selection of nodes are traversed only. And the second family of CFR modifications deals with how you combine your strategies, how you combine your regrets, so you can converge faster to Nash Equilibrium. And good analogy to understand this is consider MCCFR family of algorithms like HGD. They are noisier estimation of your gradients, but they are much faster to calculate, and you don't lose much from this added noise. And consider linear CFR family of algorithms as optimizers. They just take your screenshots of your gradients, and they combine them in a way that helps you converge much faster. And without the latter, it wouldn't be possible to have superhuman AI as well. This was a new innovation as well. Okay, this is almost the last slide, I promise. So why is this the hardest way to get rich? Actually, the field is pretty limited. Not many people are working in this field, and this is partly because there is big scarcity of educational resources. There aren't very good blog posts to understand what CFR is, what action or card abstraction is, so we had to read all of this stuff from the papers, from the sources. There are no open source good libraries for environment like OpenAI Genies for Markovian processes. There is no good implementation of card abstraction, action abstraction, subgame solving, which we didn't have time to cover, variance reduction. So I said to understand whether your bot is better than human, you have to play enormous amount of hands. The alternative is variance reduction techniques like IVAT, but there is no good implementation open source for this, and there is no good open source scalable fast implementation of CFR family of algorithms. All of the variants we found that were open source were for educational purposes and written in pure Python. The only thing actually that we found that was open source that we ended up using was a C++ implementation of hand strength evaluation. So it would tell whether this hand is stronger or that hand is stronger in any given situations. We didn't have time to discuss how we map abstractions from actual game tree to abstract game tree. We didn't have time to distract how we can find good approximation for subgame solving, and how we do evaluation, or how we solve the subgames when we separated it with enough information. These are actually pretty important topics as well. I just didn't have enough time. So did we get rich after building a poker bot? No, because it's not moral to pretend to be a human and win another player that doesn't know who he is facing. And the second reason actually is that remember at the start of the presentation I told you that we set the stake sizes to be equal for both players. This actually makes our life much easier, and this is a cleaner problem to solve. But if you want to build a bot that will beat humans in regular poker rooms, you have to configure it to be able to play from any starting stake configuration. You can't just pretend like every hand will start with equal amount of stakes. So this will blow your action space much more, and if you can build a bot that can play poker with these constraints, then you should probably go do PhD at MIT and don't waste your time scamming people online. Future directions that were very interesting. There are some neural network methods that try to do CFR. They are not very successful as of now, but they will eliminate most of the problems with card abstraction and action abstraction, because they learn these abstractions implicitly underneath, and they can form much more efficient representations from learning from the data. Okay, I want to acknowledge these people, my teammates. The both wouldn't be possible without David Petrosyan, Narek Kandanian, and Grigor Keropyan. So I want to thank them for their huge contribution. And I want to also thank Noam Brown, who invented most of the stuff that we ended up using in our bot. This researcher was kind enough to let me use his slides and almost all of his research actually in building the bot. Most of the algorithms I described were dramatically improved or straight up invented from ground up by this researcher. So this concludes my talk.
Questions? So this condition that you said about starting from different stakes, is it something that these teams do not consider yet, or?
Yeah, actually, if you think about it, it's much cleaner to not include buying as an option, because people just don't start from maximum stakes because they don't have enough money, or they don't want to go to buying each iteration. So I don't think this diminishes their research results at all. They tried to do something like that, different stakes sizes at the beginning, but it was a special case. Like it wouldn't work in all conditions, and it wasn't state of the art. So there, as far as my understanding of the current situation of research is, there is no way of doing this.
Thank you.
Okay, I have a question. Khoren, with the other reinforcement learning famous algorithms like Go and then chess, there were always some instances where the bot showed something that humans sort of didn't know about the game. For instance, with chess, AlphaZero was famously pushing side pawns much more aggressively than the computer programs before. Did you see anything like that with your bots, those sort of things in poker which were strange to you, but it makes sense because that was an equilibrium?
So, me and the team are not such good poker players to maybe draw some kind of high-level conclusions and understand the depth of the bot's knowledge. And second, I think it will be much harder to do for a poker bot because poker bot outputs probability distribution over your actions, and it's much harder to analyze probability distribution than analyzing what action should be taken in this particular position, which will be one single action. So I think smarter people than me who play poker regularly and are pros, they use this to train themselves. But as far as some distinct tactics, I don't know. Yeah, I remember actually they discovered that bot discouraged limping, which is the process when you make small bets. They discovered that the bot at the beginning started using it, but as it converts to Nash, it started not using it at all. So this is some conclusion.
Last question, and we are out of time, so please keep it short.
It's a simple question. How did you know that your bot is wins or women's? Did you test it on Poker Grossmeister or something like that?
No, we actually want to do that, but we gotten a chance to do that yet.
So are you sure that your
No, I'm not sure.
strong winner?
It's actually pretty tricky because these researchers have done almost the same things. They changed some theoretical aspects, but they had almost the same bot 2 years earlier, and the bot lost to humans because their action obstruction wasn't good enough, and their mapping from real game tree to abstract game tree and back and forth wasn't good enough. So it's possible that it might even be very close, but not good enough, or it might be good.
Okay. Thank you very much, Khoren. Thanks everyone, and quick information, there is an after party after the closing, which is open to everyone. So that's tomorrow. Which will be
Holiday Inn Republic Square.
Yeah, Holiday Inn at the Republic Square. I think we're at the rooftop, right? And the time was 8 o'clock. It's in the agenda. So not the printed one on the website. I don't know if we have updated the place yet, but you can check the time.
So bring your badges.
Bring your badges for a free drink.